Alright, cosmic voyagers, settle in. Let your limbs grow heavy, your breath slow to the rhythm of distant tides. Tonight, we're not just gazing at the familiar, comforting pinpricks of light that have lulled humanity to sleep for millennia. No, tonight we're sifting through the universe's latest batch of cosmic postcards, the fresh revelations that have our scientists blinking, scribbling furiously, and occasionally just staring into the middle distance with a look of profound, bewildered awe. These are the truths the cosmos has recently, let's say, deigned to share. The hot-off-the-press facts that are gently, or sometimes not so gently, reshaping our understanding of everything. And our first port of call on this sleepy voyage through the newly charted territories of the known, well, it involves getting your feet wet. Metaphorically, of course, mostly. We're talking about water. Oceans of it. Not just the friendly blue stuff that makes up most of our home, bless its life-giving, overfished heart. We're talking about exoplanets, worlds orbiting other suns, that are increasingly looking less like barren rocks and more like cosmic water balloons. The James Webb Space Telescope, that magnificent golden eye staring into the deepest corridors of time and space, along with its tireless ground-based colleagues, has been particularly chatty on this subject. The news? Water worlds, planets where H2O is a dominant feature, might not be the rare celestial jewels we once imagined. They might be disturbingly common, like finding pigeons in a city park or existential angst at a philosophy conference. They're just out there. Lots of them. Imagine, if you will, you're drifting towards one. Your little dream ship, quiet as a sigh, navigating the interstellar currents. Perhaps it's a pale turquoise sphere swaddled in pearlescent clouds. Or maybe it's a brooding, dark sapphire, its surface barely reflecting the dim light of a distant alien sun. It could be a planet entirely encased in a shimmering shell of ice, kilometers thick, with an ocean slumbering in the crushing, lightless depths beneath. The universe, it seems, has a particular fondness for this simple molecule, 2 parts hydrogen, 1 part oxygen. It's a cosmic staple, apparently. Easy to make, and it gets everywhere. Now, the romantic in you, the part that still believes in fairy tales with slightly better plumbing, might hear water world and think paradise. Visions of gentle waves lapping on alien shores, perhaps some bioluminescent flora, maybe even a friendly, vaguely dolphin-like creature offering you a space cocktail. And who knows? The universe is vast and deeply weird. But science, our ever so slightly cynical friend, taps us on the shoulder and whispers a few caveats. For one, water is a broad term. The water on these worlds might not be the kind you'd fill your artisanal water bottle with. Imagine an ocean under such immense atmospheric pressure that the water exists in a bizarre state called supercritical fluid, neither liquid nor gas, but something unsettlingly in between, and quite possibly corrosive enough to strip the paint, and then the hull from your imaginary dream ship. Or perhaps the water is laced with ammonia or methane, or compounds that would make our earthly extremophiles pack their tiny bags and flee screaming. The universe, you see, is a brilliant chemist but not always a considerate host. Then there's the sheer scale. A true water world might have an ocean hundreds, even thousands of kilometers deep. No land, no continents, just water. Endless, horizonless water above and below. It's a beautiful thought for about 5 minutes. Then the profound, soul-crushing loneliness of it might begin to set in. Imagine floating adrift with no anchor, no shore in sight, not just for days but for eons. It makes being stranded on a desert island look like a bustling metropolis. Narrator: a very subtle, almost imperceptible sound of distant, deep water, perhaps with a faint, melancholic hum. And what about the conditions? If there's an atmosphere, what's it like? Is it breathable or a toxic cocktail that would sear your lungs with the first inhale? What's the temperature? Are we talking a gentle, tropical bath or a scalding, pressurized cooker? Or perhaps it's a solid block of ice, as we mentioned, a global glacier locking away its secrets. To get to that hidden ocean, you'd need to drill through more ice than exists on all of Earth, facing pressures that would turn a submarine into a crumpled tin can. Suddenly, that vacation brochure for Oceanus Prime seems a little less appealing, doesn't it? Spectacular views for the 3 seconds your vessel remains intact. This isn't to say these worlds aren't wondrous. They absolutely are. The sheer fact that the universe is so profligate with the primary ingredient for life as we know it is breathtaking. It shifts the odds, doesn't it? From a lonely Earth in a dry cosmos, to a galaxy potentially teeming with dampness at the very least. Each discovery of a water-rich exoplanet is a little nudge from the cosmos, a whisper of possibility. But it's a possibility laced with the universe's typical indifference. It provides the stage, the props, the basic ingredients, and then wanders off, whistling, to explode a supernova somewhere else. Whether life takes hold, whether it thrives, whether it evolves to ponder the irony of its own wet existence, that's a different story. The universe, it seems, is perfectly happy creating countless sterile, beautiful, terrifyingly vast oceans where nothing more complex than a rogue ice crystal ever disturbs the silence. Or perhaps they are teeming with things beyond our wildest imaginings, things that find our idea of a habitable environment rather quaint and limiting. So, as you begin to drift deeper into your own quietude, picture these countless worlds. Some shimmering with liquid promise, others locked in icy stasis. Some perhaps cradle life in their depths. Others are just monumental, silent testaments to the universe's ability to make a whole lot of water. It's a beautiful, humbling, and faintly absurd thought, isn't it? The cosmos, a prolific fountain, endlessly generating these potential cradles, these vast, indifferent puddles, scattered among the stars. Are they serene oases, these newly found water worlds? Or just exquisitely rendered, deeply inhospitable expanses? The truth, as always, is likely a complex and perhaps chilling mixture of both. But for now, let the idea of these infinite waters wash over you, a gentle cosmic tide pulling you towards sleep. The universe is full of surprises, and most of them are very, very wet. And as you float on that gentle tide, leaving the image of those countless water worlds to shimmer in your mind's wake, let your awareness drift a little further, a little deeper into the cosmic revelations of our time. Our magnificent James Webb Space Telescope, not content with merely spotting these potentially soggy orbs, is now performing feats of interstellar espionage that would make even the most seasoned spy blush. It's not just seeing exoplanets, it's sniffing their air. We're talking about detailed atmospheric detections on worlds light years away. Imagine that. We're analyzing the breath of alien planets. It sounds like science fiction, doesn't it? Something whispered in hushed tones in a dimly lit observatory in a classic film. Yet here we are. By cleverly observing the light from a planet's host star as it filters through the exoplanet's atmosphere, or the light emitted by the planet itself, scientists can tease out the chemical signatures present. It's like holding a prism up to a sunbeam that has grazed an alien sky and reading the subtle story written in its spectrum. We're finding carbon dioxide, a familiar friend or foe depending on your perspective on climate change. We're finding methane, which on Earth is often, though not exclusively, linked to biological processes, or, cows. Lots of cows. We're detecting water vapor, confirming the sogginess we just discussed, hanging in alien clouds. And sometimes, just sometimes, there are tantalizing hints of more complex molecules. The building blocks. The stuff that makes astrobiologists sit up a little straighter, their coffee growing cold as they stare at the data streams. It's a profound leap, this ability. We've gone from merely cataloging dots of light to performing remote chemical assays on worlds we can never hope to visit in person, at least not with our current, rather fragile, fleshy forms. Now, as you drift, let your mind play with this. You're a cosmic detective, sifting through the spectral clues. You see the telltale dip in the light curve that signifies carbon dioxide. Interesting, you think, stroking your imaginary beard. A planet with an atmosphere thick enough to trap some heat. Could be good for life. Or it could be Venus's angrier, more distant cousin, a runaway greenhouse hellscape where lead would melt on the surface. The universe, remember, has a dark sense of humor about these things. One molecule's cozy blanket is another's infernal oven. Then a flicker indicating methane. Your eyebrow quirks. Wow. Methane can be produced by microbes, by life. It's a potential biosignature. Your heart, even in its sleepy state, might give a little flutter of excitement. But then the ever-present cosmic realist in your head clears its throat. Methane can also be produced by geological processes. Volcanoes. Weird chemical reactions in the planet's mantle. Don't get your hopes up, champ. Could just be a very gassy rock. And so, the cosmic seesaw, hope, dashed by perfectly plausible and frankly rather dull non-biological explanations. Water vapor, of course, is always a welcome sight. It confirms the presence of that crucial ingredient. But again, the quantity and state matter. Is it a humid, life-nurturing haze, or a wispy trace in an otherwise desiccating atmosphere? Is it forming gentle rain, or scouring storms of superheated steam? Details. The universe is all about the fine print, and it rarely prints it in a large, easy-to-read font. The discovery of more complex molecules, those are the real head-turners. Hints of organic compounds, the kind that, on Earth, eventually decided to get together and start the whole messy business of life. But even here, caution is the watchword. The universe is a colossal chemical laboratory. It can cook up all sorts of complicated stuff without any biological assistance whatsoever. Asteroids and comets are full of organic molecules, created by straightforward, albeit energetic, cosmic chemistry. Finding them in an exoplanet's atmosphere is thrilling, a step in the right direction, but it's not quite the smoking gun that says ET was here and left the stove on. Imagine the scene on one of these worlds, based on its atmospheric sniff test. Perhaps it's a planet bathed in the ruddy glow of a red dwarf star. Its atmosphere, thick with carbon dioxide and wisps of methane, creates a perpetual, gloomy twilight. The surface might be warmer than its distance from its dim sun would suggest, a planetary greenhouse effect in full swing. Would life arise there? Could it? Perhaps. Or perhaps it's just a sterile, albeit atmospherically interesting rock, silently absorbing its star's faint warmth. The truly unsettling part? The sheer alienness of it all. We search for biosignatures based on life as we know it. Carbon-based, water-dependent, producing certain types of gases. But what if life out there plays by entirely different rules? What if its chemical signatures are things we wouldn't even recognize as signs of life? What if its breath smells to our instruments like nothing more than mundane geology, while in reality, a silicon-based intelligence is composing symphonies in a methane sea? The limitations of our understanding, our terrestrial biases, are always a silent passenger on these voyages of discovery. We're like a dog sniffing a library, capable of detecting fascinating smells, but utterly oblivious to the stories contained within the books. And then there's the other, slightly more unnerving thought. What if we detect something unambiguously biological? Something that screams life? Not just a hint, but a clear, undeniable signal. The initial elation would be quickly followed by a cascade of rather more sobering questions. What kind of life? Is it intelligent? Is it friendly? Or is its atmospheric byproduct, so clearly indicative of life, also a warning sign? Perhaps a planet-wide industrial pollutant, a sign of a civilization that, like some we could mention, is busily fouling its own nest on a cosmic scale. The universe isn't obliged to provide us with neighbors who are good role models. So, as these spectral lines dance before your inner eye, telling tales of distant chemistries, let the ambiguity soothe you. We are peering into the unknown, catching faint whiffs of alien air. Each detection is a marvel, a testament to human ingenuity. But each one also deepens the mystery. Does that particular mix of gases mean a thriving ecosystem, a dying world, or just a peculiar set of geological coincidences? The universe keeps its secrets well, even when it seems to be exhaling them right into our telescopes. Let the uncertainty be a soft blanket. We are learning. We are exploring. But we are also profoundly, wonderfully, and perhaps a little terrifyingly ignorant. And in that vast expanse of not knowing, there is a strange kind of peace. The pressure is off. We don't have all the answers. We're just listening to the whispers, sniffing the cosmic breezes, and wondering. And as the scent of those alien atmospheres fades, a new kind of celestial entity drifts into our sleepy contemplation. We've considered worlds awash with water, worlds whose air we can remotely taste. Now let your mind wander to the loneliest inhabitants of the galaxy, the rogue planets. These are the orphans of the void, worlds unmoored from any star, drifting in the cold, interstellar darkness. For a long time we thought they were cosmic rarities, oddballs. But recent surveys and gravitational microlensing studies, clever techniques that watch for the way a foreground object's gravity bends the light of a background star, suggest there might be far more of these starless wanderers than planets comfortably nestled in solar systems, perhaps even outnumbering them. The galaxy, it seems, might be more of a cosmic orphanage than a collection of neat, tidy families. Picture it, a planet, perhaps Earth-sized, perhaps a gas giant grander than Jupiter, sailing silently through the black. No sunrise, no sunset. No seasons dictated by a leisurely orbit around a parent star. Just an eternal, star-dusted night, punctuated only by the faint, impossibly distant glow of the galactic core or the scattered shimmer of nebulae. It's a chillingly beautiful image, isn't it? A world forever cast adrift. How do these cosmic castaways come to be? The universe, in its formative years, was a rather boisterous nursery. Young solar systems were chaotic places, full of planetary pinball, gravitational tugs of war between sibling worlds. Sometimes, a smaller planet could get the cosmic equivalent of a well-aimed billiard shot, ejected from its home system entirely, flung out into the lonely dark. Other times, stars themselves might have a close encounter, disrupting each other's planetary broods. Or perhaps some stars are just terrible parents, gravitationally speaking. Less, come here little one, and more, get out and don't let the galactic plane hit you on the way out. The existence of so many rogue planets paints a picture of a dynamic, sometimes violent, galactic history. It reminds us that stability is not a given. Our own solar system, with its relatively well-behaved planets tracing their familiar paths, might be more of a fortunate exception than the rule. For every stable orbit, there might be countless stories of exile. Now, imagine the conditions on such a world. Without a star to provide warmth and light, the surface would likely be frozen solid, colder than Pluto, colder than your ex's heart after you forgot their birthday. Any atmosphere it once possessed would have long since condensed, frozen, and fallen as a permanent, motionless snow of nitrogen, oxygen, or whatever gases it once held. A silent, ice-encased tomb, drifting through the void. Sounds delightful for a weekend getaway, doesn't it? Visit Planet Rogue X7. Experience absolute zero and the crushing weight of existential despair. Bring your own thermal underwear. And therapist. And here's where the universe always throws in a strange little twist. Even these frozen orphans might not be entirely devoid of interest. If a rogue planet is large enough, its core could still be hot due to residual heat from its formation, or from the slow decay of radioactive elements within its mantle. The same processes that keep Earth's own core molten. This internal heat could potentially sustain a subsurface ocean of liquid water, hidden beneath kilometers of insulating ice. Life in such an ocean? It's a long shot, a very long shot. No sunlight for photosynthesis. Just chemical energy seeping from hydrothermal vents, perhaps. But the universe has surprised us before. Life, as we've grudgingly learned, can be stubbornly persistent in the most unlikely of places. Imagine an entire biosphere evolving, living, and dying in utter darkness, on a world that doesn't even know what a sun is. It makes our own sun-drenched existence seem almost ostentatiously privileged. And then there's the sheer number of them. If rogue planets are indeed more common than homed planets, it means the galaxy is littered with these dark wanderers. Billions, perhaps trillions of them. Most are probably cold, dead rocks or ice balls. But statistically, among that vast multitude, could there be some that are different? Perhaps a gas giant rogue with a retinue of moons, one of which is kept warm by tidal forces, like Jupiter's Europa or Saturn's Enceladus, but without any Jupiter or Saturn in sight. A little pocket of warmth, a tiny oasis of possibility, drifting alone. The thought of these rogue planets also brings a certain philosophical chill. They are a stark reminder of cosmic loneliness. What is it like to be a world without a sun? To have no central anchor, no celestial rhythm to your days, if you could even call them days? It's the ultimate cosmic solitude. It makes our own brief moments of human loneliness seem rather trivial in comparison. We fret about being alone in a room. These worlds are alone in a galaxy. There's a certain bleak poetry to it. These planets, ejected from the warmth and light of their birth systems, carry on. They endure. They are testament to the universe's grand, indifferent sweep. They are the celestial embodiment of moving on. Or perhaps, being violently kicked out and having no choice but to move on. Details. So, as you drift deeper into your rest, let your mind accompany one of these lonely wanderers for a while. Feel the profound cold, the absolute silence, broken only by the faintest whisper of gravitational tides from distant stars it will never truly know. There's a strange peace in that absolute desolation, a release from the hustle and bustle of sunlit worlds. These rogue planets are the universe's quiet rebels, its silent drifters, each carrying its own frozen secrets through the endless night. They are a reminder that not everything needs a star to have a story, even if that story is written in degrees Kelvin and eons of darkness. And perhaps, in their vast, cold, unlit numbers, they hold clues to the galaxy's chaotic past and its ultimately unknowable future. They are the orphans of the void, yes, but they are also, in their own way, free, unbound, subject only to the grand, slow dance of galactic gravity. And there's a certain stark beauty in that, a chilling, liberating truth for a mind seeking the quiet of deep sleep. From the cold, silent drift of rogue planets, let our journey now take us towards something altogether more intense. Something that doesn't just wander the void, but actively shapes it, consumes it, and inspires a unique blend of scientific awe and primal fear. We're turning our sleepy gaze towards black holes, specifically, the recent triumphs in actually seeing these cosmic monsters. For decades, they were the stuff of pure theory, mathematical phantoms lurking in Einstein's equations. We knew they should exist, their gravity so immense that nothing, not even light, could escape. But seeing is believing, as they say, even if seeing in this context involves a global network of telescopes working in concert to capture the shadow of an invisible beast. And see them we did. First, in 2019, the Event Horizon Telescope collaboration unveiled the iconic image of the supermassive black hole at the heart of galaxy M87, a fuzzy, fiery orange donut, a ring of superheated gas swirling around a central darkness. Then, in 2022, they did it again, this time capturing Sagittarius A*, pronounced A*. For those of you keeping score at home or trying to impress someone at a very niche party, the behemoth lurking at the center of our own Milky Way galaxy. These weren't artists' impressions. These were photographs. Indirect, yes, as you can't photograph something that eats light, but they were images of the Event Horizon's silhouette, the point of no return, outlined by the glowing plasma caught in its gravitational snare. Imagine the scene. Hundreds of scientists, years of work, petabytes of data flown around the world on hard drives because the internet wasn't big enough. All to catch a glimpse of nothingness. Or rather, the edge of nothingness. It's beautifully ironic, isn't it? One of humanity's greatest observational achievements is to photograph a lack of light. Let this image form in your mind. That ring of fire. It's not the black hole itself burning. Black holes, by definition, are black. That light is from matter, gas, dust, unlucky stars, being accelerated to near light speed as it spirals into the abyss. It's heated to billions of degrees, a cosmic death scream rendered in radio waves. The central dark patch? That's the shadow of the black hole, the region from which light can no longer escape. It's the visual confirmation of a concept that bends the mind, a place where space-time itself is so warped, so twisted, that all paths lead inwards. No exit. Not even for light, the universe's speed champion. Talk about a one-way street. A very, very final one-way street. These images are profound for so many reasons. They confirm Einstein's theory of general relativity in the most extreme environment imaginable. His equations, scribbled down over a century ago, predicted the size and shape of these shadows with astonishing accuracy. It's a beautiful moment when human intellect, armed with mathematics, can foresee the features of such an alien and extreme phenomenon billions of light years away. It almost makes you forgive humanity for reality television. Almost. But beyond the scientific triumph, there's the sheer existential weight of these images. We are looking at the ultimate cosmic predators. M87's black hole is 6.5 billion times the mass of our Sun. Sagittarius A** is a more modest 4 million solar masses. These are not just objects. They are gravitational overlords shaping the destinies of entire galaxies. The stars in the center of our galaxy don't just meander. They perform a frantic high-speed dance around an invisible partner, Sagittarius A*. Their orbit's a testament to its immense gravitational pull. It's like watching a cosmic maypole dance where the pole is an infinitely dense, invisible maw of spacetime. Cheerful. There's a stark beauty to it, a terrifying symmetry. The universe creates these points of ultimate consumption, these singularities where our known laws of physics break down. They are the universe's ultimate recyclers, perhaps, or maybe just its grand, dark drains. What happens to matter that falls in? We don't know. Does it get crushed into an infinitely dense point? Does it emerge somewhere else in another universe as science fiction loves to imagine? The universe, as usual, remains tight-lipped, offering only that enigmatic dark circle against a backdrop of incandescent doom. And it's right there. Sagittarius A*, in the heart of our galaxy. Our galactic home has a monster in its basement. A relatively quiescent monster, thankfully for now. But it's there. Roughly 26,000 light years away. Close enough to study, far enough, we hope, to not be an immediate existential threat. Though immediate on cosmic timescales is a rather flexible term. So, as you drift, picture that fiery ring, that central darkness. It's a glimpse into the abyss, a portrait of gravity's ultimate triumph. It's a reminder that the universe contains objects of such staggering power and density that they defy easy comprehension. They are beautiful in their starkness, in their perfect adherence to physical law, even as they represent the utter annihilation of anything that strays too close. They are the ultimate no trespassing signs of the cosmos. Strangely calming in a way. Confronting the image of something so utterly cosmically powerful, so far beyond our ability to influence or control. It puts our everyday anxieties into a rather sharp perspective, doesn't it? Worried about that email you have to send? M87's black hole just swallowed a star system for a light snack and didn't even burp. It's a universe of truly epic indifference, and sometimes, embracing that indifference is the quickest path to peace. Gaze into the void, and the void, well, it's too busy accreting matter to gaze back with any particular interest in you. And that, my friends, can be wonderfully, deeply relaxing. Having peered into the fiery maw of actively feeding supermassive black holes, let's now quiet our journey just a touch, and consider their more subtle siblings. Or perhaps the same beasts in a different mood. Science has been increasingly aware that these galactic centers, these gravitational titans, aren't always in full-on devour the universe mode. They can go through phases. They can be dormant, lying in wait, and then sometimes they can awaken. It's like realizing the seemingly placid volcano in your holiday destination's postcard is, in fact, just napping. A very, very big nap, with potentially galaxy-altering consequences upon waking. Imagine Sagittarius A*, our own Milky Way central black hole. For the most part, it's relatively quiet. It's not currently feasting on vast clouds of gas or unfortunate stars with the dramatic flare of M87 star. It's more like a sleeping giant, occasionally snacking on a small tidbit of gas or a wayward asteroid, causing faint flickers and flares that our telescopes can detect. These are like the giant's sleepy murmurs, little burps in the cosmic silence. Astronomers study these flickers intensely, trying to understand the black hole's current diet and activity levels. It's like being a cosmic zookeeper, cautiously observing the giant panda, hoping it remains content with its bamboo and doesn't suddenly develop a taste for, say, the entire solar system. But the evidence from other galaxies, and even from the history of our own, suggests that this peace is not necessarily permanent. Supermassive black holes can awaken if a large supply of fuel, a massive gas cloud, or a star straying too close, gets drawn into their gravitational embrace. When this happens, the black hole roars back to life. The accretion disk, that swirling vortex of superheated matter we saw in the M87 image, flares up with incredible intensity. Powerful jets of plasma can erupt from the black hole's poles, blasting out into intergalactic space for millions of light years. These are called active galactic nuclei, or AGN, and they are some of the most energetic phenomena in the universe. A galaxy with an AGN isn't just a gentle swirl of stars. It's a cosmic lighthouse, or perhaps more accurately, a cosmic flamethrower, visible across billions of light years. The thought that our own galactic center could theoretically flare up like this is, well, it's something to ponder as you drift off to sleep. It's not predicted to happen anytime soon, thankfully. The supply of gas near Sagittarius A* is currently quite sparse. But the universe plays a long game. Stars and gas clouds move. Galactic dynamics shift. What's quiet today could be ferociously active in a few million or a few 100 million years. Our current calm might just be an interlude, a cosmic siesta between more dramatic epochs. Makes you want to get all your important errands done, doesn't it? Just in case. Scientists find dormant black holes by looking for their gravitational influence on nearby stars, as we do with Sagittarius A*, or by catching those occasional faint flickers of activity. Sometimes they find evidence of past awakenings, giant bubbles, or lobes of plasma extending far above and below a galaxy's disk, remnants of ancient jets from a previously active central black hole. It's like finding ancient volcanic caldera, evidence of a past eruption that reshaped the landscape, even if the volcano itself is currently quiet. Our own Milky Way has such structures, the Fermi bubbles, hinting at a more boisterous youth for Sagittarius A*. It seems our galactic monster wasn't always so sleepy. This cycle of dormancy and awakening has profound implications for the evolution of galaxies. When a black hole awakens and blasts out those powerful jets, it can clear out gas and dust from the galaxy's central regions, potentially shutting down star formation. Or paradoxically, the shockwaves from the jets can compress gas clouds further out, triggering new bursts of star birth. It's a complex feedback loop, the black hole acting as a kind of cosmic thermostat, or perhaps a very temperamental landlord, periodically renovating the galactic neighborhood with extreme prejudice. So, as you lie there, feeling the gentle pull of your own bed, imagine these sleeping giants at the hearts of distant galaxies. Some are truly quiescent, perhaps for eons. Others are just lightly dozing, prone to occasional energetic outbursts if disturbed. And some, once dormant, are now in the process of reawakening, their accretion disks slowly igniting, heralding a new era of cosmic fireworks. There's a certain suspense to it, isn't there? Like watching a very, very slow-motion cosmic drama unfold, where the actors are billions of solar masses and the stage is an entire galaxy. It's another one of those cosmic truths that can be both awe-inspiring and faintly unsettling. The universe is not a static painting. It's a dynamic, evolving, and sometimes explosively energetic place. Even the most massive, seemingly immutable structures can change, can sleep, and can awaken with terrible power. Our own little corner of the Milky Way enjoys a period of relative calm, for which we should probably be grateful. It allows for things like, civilization and uninterrupted sleep. But the knowledge that these cosmic powerhouses exist, that they cycle through states of activity, adds another layer to our understanding of the universe's grandeur and its potential for sudden, dramatic transformation. It's like knowing there's a dragon curled up in the mountain cave. Mostly it sleeps, and we hope it continues to do so. But the sheer potential, the stored energy, the memory of past roars, that adds a certain frisson to the quiet of the night. Sweet dreams. And maybe, just maybe, hope that Sagittarius A* has set its alarm for a few billion years from now. At least. Having contemplated the slumbering and occasionally awakening giants at galactic cores, let our sleepy awareness now tune into a different kind of cosmic announcement, a more subtle, yet profoundly significant signal rippling across the fabric of space-time itself. We're talking about gravitational waves, those faint tremors in reality predicted by Einstein, and specifically the increasing evidence for mergers of a more elusive class of black holes, the intermediate mass black holes or IMBHs. These are the middle children of the black hole family, more massive than the stellar mass black holes born from collapsing stars, but not quite reaching the supermassive status of their galactic center cousins. And finding them, especially finding them in the act of merging, has been a fascinating and gravitationally loud detective story. For a long time, IMBHs were largely theoretical. We had good evidence for the small ones, a few to a few tens of solar masses, and the supermassive ones, millions to billions of solar masses, but the ones in between, say, a few hundred to a few 100,000 solar masses, were conspicuously absent from our cosmic senses. It was a puzzling gap. Did nature just not like making black holes in that size range? Or were they simply harder to find? The universe, as it turns out, is quite good at hiding its medium-sized monsters. Enter LIGO, Virgo, and CAGRA, the Laser Interferometer Gravitational Wave Observatory and its international partners. These incredible instruments are essentially giant L-shaped rulers, using lasers to measure tiny, almost infinitesimal stretches and squeezes in space-time caused by passing gravitational waves. When two massive objects, like black holes or neutron stars, spiral into each other and merge, they create a crescendo of these waves, a chirp, that travels across the universe at the speed of light. It's like throwing two very, very heavy rocks into the cosmic pond and watching for the ripples thousands of miles away, except the pond is space-time and the ripples are distortions in reality itself. No big deal. And in recent years, among the growing catalog of detected gravitational wave events, some have stood out. The chirps have indicated mergers involving objects more massive than typical stellar black holes, pushing into that IMBH range. One of the most notable was GW190521, a signal detected in 2019. The analysis suggested it came from the merger of two black holes, one about 85 times the mass of the Sun, and the other about 66 times. They combined to form a black hole of about 142 solar masses, releasing an enormous amount of energy in the form of gravitational waves. That 142 solar mass remnant sits squarely in the IMBH category. It was like hearing the distinct baritone roar of a previously unseen predator in the cosmic jungle. These detections are incredibly exciting because they start to fill in that missing piece of the black hole puzzle. How do supermassive black holes get so supermassive? One theory is that they grow by swallowing gas and stars, but another is that they grow by merging with other black holes, starting with smaller ones that combine to form IMBHs, which then continue to merge and grow. Finding these intermediate steps, these IMBH mergers, provides crucial evidence for this hierarchical growth model. It's like finding the adolescent pictures of the universe's biggest bullies. Imagine the scene of such a merger in your mind's quiet theater. Two black holes, already monstrous by stellar standards, locked in a gravitational death spiral. They orbit each other faster and faster, closer and closer, warping spacetime around them like a taffy pull. In the final moments, they are moving at a significant fraction of the speed of light, two patches of absolute darkness dancing a furious jig before coalescing into an even larger patch of darkness. The energy released in that final fraction of a second, not as light, but as gravitational waves, can outshine all the stars and all the galaxies in the observable universe combined, just for that fleeting moment. It's an event of unimaginable violence, yet it happens in perfect silence in terms of sound. Only the fabric of spacetime itself rings. And we, on our little blue planet, billions of light years away, billions of years later, can detect that ancient shudder. It's a testament to both the raw power of the universe and the almost absurd sensitivity of human ingenuity. We're listening to the echoes of cosmic smash-ups that happened before Earth even formed. It's a form of cosmic archaeology, where the artifacts are ripples in reality itself. The existence of IMBHs also raises other tantalizing questions. Where do they like to hang out? Some theories suggest they might be found at the hearts of smaller dwarf galaxies, or perhaps in dense globular clusters, those ancient, tightly packed swarms of stars that orbit larger galaxies like our Milky Way. If an IMBH lurks in the core of a globular cluster, it could explain some of the strange dynamics observed in those crowded stellar cities. It would be the biggest fish in a very old, very star-filled pond. So, as you relax, let the idea of these spacetime shudders gently massage your awareness. The universe isn't just visually spectacular, it has a soundtrack, albeit one written in the language of gravity. Each detected chirp is a new note in that symphony, telling a story of cosmic collision, of creation through destruction, as smaller black holes merge to form larger ones. It's a reminder that even the most enigmatic objects in the cosmos are part of an ongoing process of evolution and change. These gravitational whispers from colliding intermediate mass black holes are like messages in a bottle, thrown into the cosmic ocean eons ago, finally washing up on our scientific shores. They speak of a universe that is constantly churning, merging, and rebuilding itself, even in its darkest, most massive corners. It's a universe where even the void itself can tremble with the force of ancient embraces. And in that trembling, in that deep, silent song of gravity, there is a profound and strangely peaceful sense of connection to the universe's grand, unfolding drama. Leaving the gravitational echoes of merging black holes to fade into the quiet hum of the cosmos, let's now cast our sleepy gaze much, much further back in time, to the very dawn of cosmic history. Thanks once again to our friend, the James Webb Space Telescope, we are getting our first, somewhat blurry, but utterly astonishing baby pictures of the universe. JWST, with its incredible sensitivity to infrared light, can peer through the dust and gas that obscures visible light, and detect the faint glow of galaxies that formed just a few 100 million years after the Big Bang. That's like looking back over 13 billion years, to when the universe was just a toddler, barely out of its cosmic crib. And what we're seeing is, well, it's making some of the grown-up cosmologists spill their coffee. For a long time, our models of early galaxy formation suggested a gradual process. Small, wispy proto-galaxies forming first, slowly merging and growing over billions of years into the grand spirals and massive ellipticals we see today. It was a nice, orderly picture. The universe as a patient gardener, slowly cultivating its galactic blooms. But JWST's early dispatches from the cosmic frontier are painting a somewhat different, more precocious picture. It's finding galaxies that are surprisingly big, surprisingly mature, surprisingly bright. They appear to have formed more stars and accumulated more mass, much earlier than our previous models predicted. It's like looking at a baby picture of your distinguished, gray-haired Uncle Algernon and finding him already sporting a full beard and a monocle, and possibly complaining about the quality of the cigars in the nursery. These early galaxies seem to have bulked up incredibly quickly. Imagine the light from one of these ancient galaxies finally reaching JWST's golden mirrors. It has traveled for over 13 billion years. When that light began its journey, our own sun hadn't even been born. Earth was just a twinkle in the cosmic dust cloud's eye. The universe itself was a fraction of its current size, denser, hotter, and filled with a fog of neutral hydrogen that hadn't yet been cleared by the first starlight. And yet, through that primordial haze, JWST is detecting these surprisingly substantial structures. This is causing a delightful stir in the astronomical community. Challenging older models is the polite way to put it. Some might say it's sending theorists back to their blackboards, muttering about star formation efficiencies and feedback mechanisms. It doesn't mean the Big Bang is wrong, not at all. But it does mean that the processes that govern the birth and early growth of galaxies might have been more rapid, more intense, or perhaps just different than we thought. The universe, it seems, was in a bit of a hurry to get the galactic show on the road. No time for gradualism, folks. We've got stars to make and supermassive black holes to feed. What could be causing this accelerated development? Perhaps the conditions in the early universe, the density of gas, the nature of dark matter halos in which these galaxies formed, were even more conducive to rapid star birth than we calculated. Maybe the first generations of stars, which we'll touch on next, were so massive and energetic that their explosive deaths and the heavy elements they forged kickstarted galaxy growth in a more vigorous way. Or, and this is where it gets really interesting, perhaps there's some new physics at play, something about the fundamental nature of dark matter or early cosmic expansion that our current theories haven't quite grasped. The universe loves to keep a few aces up its sleeve. This isn't a crisis for cosmology, it's an opportunity. It's what science is all about. You build a model, you make predictions, you go out and observe. If the observations don't quite fit, you don't throw a tantrum, well, maybe a small, private one. You refine the model. You learn something new. These surprisingly mature baby galaxies are like unexpected, fascinating clues left at the scene of the universe's earliest moments. They're whispering secrets about how it all got started, if only we can learn to interpret their ancient light correctly. So, as you settle deeper into your rest, picture this. The universe in its infancy, not as a quiet, slowly stirring nursery, but perhaps as a surprisingly raucous playground, where galaxies sprang up with youthful exuberance, already shining brightly in the cosmic dawn. It's a more dynamic, more energetic picture of our cosmic origins. It reminds us that even our grandest theories are just approximations, constantly being refined by new data, new glimpses into the profound depths of time and space. These ancient, surprisingly robust galaxies are like finding a fully developed oak tree where you expected to see only an acorn. It's a puzzle, a mystery, and a beautiful testament to the universe's capacity to surprise us, to keep us humble, and to constantly rewrite its own biography. Let the light from these distant primordial structures be a soft, ancient lullaby, carrying you back towards the very beginning of everything, where the rules were still being written, and the cosmos was already busy exceeding our expectations. It's a universe that was born ready, it seems. Born to shine. Following those surprisingly grown-up baby galaxies, let's zoom in a little into the stellar nurseries of that ancient epoch, and consider the stars themselves. The latest evidence, again significantly boosted by the capabilities of JWST and sophisticated computer simulations, suggests that the very first stars to ignite in the universe, the so-called population 3 stars, may have formed in ways that were subtly, and sometimes dramatically, different from how stars like our sun are born today. These weren't your friendly neighborhood yellow dwarfs. These were, potentially, the universe's first rock stars. Bigger, brighter, hotter, and living very fast, very explosive lives. First born, and perhaps first to burn out in spectacular fashion. Imagine the universe a few 100 million years after the Big Bang. It's still mostly hydrogen and helium, the simplest elements forged in the initial cosmic fireball. The heavier elements, the carbon, oxygen, iron that make up planets like Earth and beings like us, barely existed yet. They had to be cooked up in the hearts of stars. And these first stars, these population 3 pioneers, were the original cosmic chefs. Because the primordial gas clouds from which they condensed lacked these heavier metals. In astronomical parlance, anything heavier than helium is a metal, which always amuses geologists. The physics of their formation was different. Metals act like cooling agents in gas clouds, helping them radiate away heat, fragment, and collapse into many smaller stars. Without these metals, the primordial clouds might have collapsed more monolithically, forming stars that were, on average, much more massive than stars forming today. We're talking potentially hundreds, even up to 1,000 times the mass of our Sun, absolute behemoths. Picture one of these giants igniting in the dark, pristine early universe. It would have been incredibly luminous, blazing with a fierce blue-white light, pumping out vast amounts of ultraviolet radiation. These weren't gentle, twinkling lights. They were cosmic blast furnaces. Their surfaces would have been scorchingly hot, their stellar winds ferociously powerful. They would have been relatively short-lived precisely because they were so massive. The bigger they are, the harder they burn, and the faster they exhaust their nuclear fuel. While our Sun will enjoy a leisurely 10 billion-year lifespan, these population 3 monsters might have blazed through their entire existence in just a few million years, a mere cosmic eye blink. And their deaths? Oh, their deaths would have been something to behold. Not the relatively gentle puffing off of outer layers that await stars like our Sun. Many of these first stars, due to their immense mass, would have likely collapsed directly into black holes, perhaps forming the seeds for the supermassive black holes we see later. Others might have exploded as pair-instability supernovae, a particularly violent type of stellar explosion that occurs in very massive stars, so powerful that they leave no remnant behind, no neutron star, no black hole, just an expanding cloud of freshly synthesized heavy elements. They literally blew themselves to smithereens, scattering their precious cargo of carbon, oxygen, silicon, and iron into the surrounding void. It's these explosive deaths that were crucial for the subsequent evolution of the universe. These were the first significant polluters of the cosmos, but in a good way. They seeded the primordial gas clouds with the heavy elements necessary for later generations of stars, like our population 2 and population 1 stars, including the Sun, to form with a richer chemical palette. And, crucially, these heavier elements allowed for the formation of dust grains, which are essential for the formation of planets. Without the ashes of these first giant short-lived stars, there would be no rocky planets, no Earth, no us. We are, quite literally, made of the recycled guts of these ancient, explosive pioneers. It's a rather visceral yet strangely poetic form of cosmic ancestry. Thanks for exploding so comprehensively, great-great-grand star. Finding direct observational evidence of these population 3 stars is incredibly challenging. They are long gone, having burned out billions of years ago. But astronomers search for their indirect chemical signatures in the oldest, most metal-poor stars still around today, or in the composition of distant gas clouds illuminated by quasars. JWST, with its ability to see the very earliest galaxies, might even catch glimpses of the collective light from regions where these first stars were forming in vast numbers, or the characteristic glow of nebulae ionized by their intense radiation. So, as you drift in the quiet darkness, imagine these first cosmic beacons. Solitary giants, or perhaps small clusters of them, igniting in a universe still largely untouched by complex chemistry. They were the trailblazers, the ones who started the process of cosmic enrichment. Their fierce lives and even fiercer deaths were not just spectacular light shows. They were transformative events, fundamentally changing the character of the universe, paving the way for everything that came after. There's a certain stark grandeur to this idea. The universe needed these sacrificial giants, these short-lived titans, to create the building blocks for future complexity, for future life. They were born of simple stuff, lived lives of incredible intensity, and then generously, if explosively, donated their hard-won elemental treasures to the cosmos. It's a cycle of creation born from fiery destruction, a fundamental rhythm of the universe. The first to burn, yes, but also the first to give. And in that grand, selfless act of cosmic alchemy, there's a strange, profound comfort, a sense of being connected to the very first light, the very first explosions that shaped the universe we inhabit today. From the fiery birth and death of the universe's first stars, let's now zoom out again, not in time but in scale, to contemplate one of the largest, yet most elusive structures in the cosmos, the cosmic web. For decades, cosmological simulations have predicted that matter in the universe, both ordinary matter, like us and galaxies, and the mysterious dark matter, isn't distributed randomly. Instead, it should be arranged in a vast, interconnected network of filaments, clusters, and voids, like a gigantic, ghostly spiderweb stretching across billions of light-years. And recent observations, including those from deep galaxy surveys and studies of the intergalactic medium, are bringing this cosmic web into sharper, albeit still faint, focus. We're beginning to trace the filaments of this unknown, largely invisible scaffold upon which the universe is built. Imagine looking at the universe on the grandest possible scale. Galaxies aren't just scattered like dust motes in an empty room. They tend to congregate. They form groups, then clusters of galaxies, and then superclusters, enormous congregations of thousands of galaxies. But these clusters and superclusters aren't isolated islands. They appear to be connected by long, tenuous bridges or filaments of matter, primarily dark matter, but also laced with diffuse hydrogen gas. In between these filaments and clusters are vast, relatively empty regions called cosmic voids, like giant bubbles in the cosmic foam. This intricate, three-dimensional lacework is the cosmic web. Dark matter, which we'll grapple with more directly a little later, is the dominant gravitational player here. It doesn't interact with light, hence dark, but its gravity sculpts the universe. The cosmic web is essentially the skeleton of dark matter, and the galaxies we see are like the brightly lit cities that have sprung up along its densest pathways and intersections. The ordinary, luminous matter has simply fallen into the gravitational wells created by the dark matter. We're basically living in the decorated parts of an invisible architectural marvel. Comforting, isn't it? Knowing that the vast majority of the universe's scaffolding is made of something we can't see and don't understand. It's like living in a house designed by a very shy, very powerful ghost. Observing these filaments directly is incredibly difficult. They are so diffuse, so faint. But astronomers are clever. One technique involves looking at the light from distant quasars, those incredibly bright, active galactic nuclei we touched upon. As the quasar light travels across billions of light-years towards us, it passes through these intergalactic filaments. The hydrogen gas in the filaments absorbs some of the quasar light at specific wavelengths, creating a kind of forest of absorption lines in the quasar spectrum. By studying these absorption lines from many different quasars in different directions, astronomers can start to map out the distribution of this diffuse gas, and thus, infer the underlying structure of the cosmic web. It's like feeling for the shape of an invisible object by observing how it subtly affects things passing through it. Other methods involve looking for the faint glow of hydrogen gas within the filaments themselves, either through its emission or by how it scatters light from nearby galaxies. JWST is also expected to contribute here by being able to detect very faint, distant galaxies that might be forming along these filaments in the early universe, acting like breadcrumbs tracing the web structure. The cosmic web isn't just a pretty pattern. It plays a crucial role in the evolution of galaxies. These filaments act as cosmic highways, funneling gas towards the denser regions where galaxies form and grow. Galaxies aren't just passively sitting there. They are constantly accreting fresh gas from these intergalactic streams, fuel for new star formation. It's like a galactic irrigation system, ensuring that the stellar nurseries don't run dry. Sometimes, galaxies can also migrate along these filaments, eventually merging with other galaxies at the dense intersections, the cosmic cities, known as galaxy clusters. So, as you relax and let your thoughts drift, try to visualize this immense, ethereal structure. Billions of light years across. Filaments of invisible dark matter, threaded with wisps of primordial hydrogen, connecting glittering clusters of galaxies. Vast, dark voids in between regions of profound emptiness. It's the universe's grand architecture, a design laid down by gravity acting on the subtle density fluctuations present in the very early cosmos. There's a sense of immense scale here that is both humbling and strangely beautiful. Our own Milky Way galaxy is not an isolated entity. It's part of this web, residing in a filament that connects us to the Virgo supercluster and beyond. We are connected, quite literally, by these invisible threads of matter to the rest of the cosmos. It's a rather profound thought, isn't it? This vast, dark, largely unseen network underpins everything. And it's mostly made of stuff we don't understand. That's the kicker, the little cosmic joke. We're mapping this grand design, marveling at its elegance and its crucial role in cosmic evolution, all the while acknowledging that the primary building material is a complete mystery. It's like admiring a magnificent cathedral, and then being told it's mostly constructed from solidified anxiety and existential doubt. You'd still admire the architecture, but perhaps with a slightly more quizzical and wry expression. Let the image of this ghostly grand design soothe you. It's a reminder of the underlying order, the hidden structures that shape the universe, even if those structures are predominantly invisible and composed of the unknown. It speaks to a universe that is far more interconnected, far more intricately woven, than our everyday experience might suggest. We are all, in a very real sense, caught in the cosmic web. And for tonight at least, that's a rather comforting, sleep-inducing place to be. Having contemplated the vast, shadowy architecture of the cosmic web, let's bring our journey a little closer to home, though still venturing out into the chilly suburbs of our own solar system. We're going to skate across the surfaces of icy moons and distant dwarf planets, worlds that we once thought were cold, dead, and geologically uninteresting. But recent missions and observations have revealed a surprising truth. Many of these frosty bodies are anything but inert. They are crackling, spewing, and groaning with unexpected geological activity. It seems even in the deep freeze of the outer solar system, there are hidden fires, or at least hidden slushiness. Think of Saturn's moon Enceladus, a relatively small, ice-covered world, just 500 kilometers in diameter. For a long time, it was just another point of light. Then the Cassini spacecraft arrived and gave us a close-up look. And what did it find? Giant plumes of water ice, water vapor, and organic molecules erupting from cracks near its south pole, venting material from a subsurface ocean hundreds of kilometers into space. These cryovolcanoes, ice volcanoes, were a stunning discovery. Enceladus wasn't just a snowball. It was an active, dynamic world with a liquid water ocean sloshing beneath its icy shell, kept warm by tidal forces generated by Saturn's immense gravity. Suddenly, this tiny moon became one of the prime candidates for finding extraterrestrial life within our own solar system. Not bad for a place that looks, from a distance, like a well-polished billiard ball. Then there's Jupiter's moon Europa, another ice-encased world with strong evidence for a vast global ocean beneath its frozen crust. While we haven't seen plumes as dramatic as Enceladus's, though there have been tantalizing hints, Europa's surface shows chaotic terrain, fractured ice sheets, and features that suggest upwelling warmer ice or even occasional breaches of liquid water to the surface. It's like watching a frozen pond in spring, with cracks and groans as the ice shifts and groans over the water below. Future missions like Europa Clipper aim to investigate this ocean's potential habitability. The thought of what might be swimming in those dark, cold alien waters is enough to give you a little shiver, isn't it? Hopefully, it's just very, very lost space shrimp, and not something that considers nuclear submarines a light snack. And it's not just moons of giant planets. Even Pluto, way out in the Kuiper Belt, dethroned from planethood but no less fascinating for it, surprised us. When the New Horizons spacecraft flew past in 2015, it revealed a stunningly diverse and geologically active landscape. Vast plains of nitrogen ice, towering mountains of water ice, and evidence of cryovolcanoes that may have erupted slushy mixtures of water, ammonia, or methane. Pluto, once considered a cosmic ice cube at the edge of nowhere, turned out to be a complex, evolving world, with internal processes still shaping its surface, billions of years after its formation. It's like finding out your quiet, elderly great-aunt is secretly a champion ice climber. What's driving all this unexpected activity? Tidal heating, as mentioned for Enceladus and Europa, is a major factor for moons orbiting giant planets. The constant flexing and stretching from gravitational tugs generates friction and heat within the moon's interior, enough to melt ice and maintain liquid oceans. For more distant bodies like Pluto, the decay of radioactive elements in their cores could provide a long-lasting internal heat source, similar to what happens inside Earth. And the presence of substances like ammonia or methane mixed with water can act like antifreeze, allowing liquids to exist at much lower temperatures than pure water would. The universe, it seems, is very good at finding ways to keep things fluid even in the most unpromising, frigid conditions. This flurry of activity on icy worlds is profoundly exciting for astrobiologists. Liquid water is, as far as we know, a key ingredient for life. And if these subsurface oceans exist, protected from harsh radiation by thick ice shells, and potentially supplied with chemical energy from hydrothermal vents on their ocean floors, much like those found in Earth's deep oceans, then they represent potentially habitable environments right here in our cosmic backyard. It's a much more optimistic picture than the old view of a solar system with only one potentially life-bearing oasis. Suddenly, our solar system looks less like a desert with a single well, and more like a landscape with numerous hidden springs and subterranean lakes. So, as you lie there warm and comfortable, imagine these distant, icy realms. Picture the geysers of Enceladus, glittering curtains of ice crystals catching the faint sunlight, raining back down onto a fractured, icy plain. Imagine the groaning, shifting ice sheets of Europa, hinting at the vast, dark ocean beneath. Feel the surprising warmth emanating from the heart of distant Pluto, driving slow, majestic cryovolcanic eruptions of exotic ices. These aren't just static, frozen museum pieces. They are living worlds in their own icy way. They whisper of hidden warmth, of unexpected dynamism, of the persistent ability of nature to create pockets of activity and potential even in the most extreme cold. It makes our own winter complaints about a bit of frost on the car seem rather quaint, doesn't it? Oh dear, a light dusting of snow. Meanwhile, on Triton, nitrogen geysers are erupting 8 kilometers high. Perspective. Let the thought of these active icy bodies soothe you into a state of deep relaxation. They remind us that the universe is full of surprises, that even the places we assume are barren and unchanging can harbor secret wonders, hidden oceans, and the subtle pulse of geological life. The cold out there is profound, yes, but it's not always absolute. There are pockets of warmth, of movement, of possibility, even in the deepest, darkest, iciest corners of our solar system. From the surprisingly lively icy moons of the outer solar system, let's now turn our attention to some of the smaller, often overlooked, but incredibly important residents of our cosmic neighborhood, the asteroids and comets. These aren't just passive rocks and dirty snowballs aimlessly wandering between planets. They are time capsules, remnants from the very birth of our solar system, over 4.5 billion years ago. And thanks to incredibly ambitious sample return missions like Japan's Hayabusa 2, which visited asteroid Ryugu, and NASA's OSIRIS-RX, which visited asteroid Bennu, we're not just studying them from afar anymore. We're bringing pieces of them back to Earth, holding ancient cosmic history in our laboratory hands. And what these samples are telling us is refining, and sometimes revolutionizing, our understanding of how our solar system, and perhaps even life on Earth, came to be. Imagine these missions. Robotic spacecraft traveling hundreds of millions of kilometers, performing intricate dances around tiny, irregular rubble pile asteroids. They map the surface in exquisite detail, then, with breathtaking precision, descend to gently touch the surface, or, in OSIRIS-REx's case, give it a rather enthusiastic high five that kicked up a lot of material, and collect a few precious grams of dust and rock. Then they journey all the way back to Earth, deploying a sample capsule to streak through our atmosphere and parachute gently down to a designated landing zone. It's an astonishing feat of engineering and navigation, all for a thimbleful of space dirt. But oh, what that dirt can tell us. The analysis of these return samples is like opening a perfectly preserved treasure chest from the dawn of the solar system. These asteroids, particularly primitive ones like Ryugu and Bennu, haven't undergone the intense geological processing that planets like Earth have. They haven't been melted, differentiated, or weathered nearly as much. So, they preserve a much clearer record of the initial ingredients that made up the protoplanetary disk from which everything in our solar system formed. What are we finding? 4.1 An abundance of water-rich minerals. Clay minerals, hydrated silicates, rocks that have chemically bound water within their structure. This provides strong evidence that water was plentiful in the early solar system, even in the regions where these asteroids formed. It bolsters the theory that asteroids and comets, through countless impacts in Earth's early history, could have delivered a significant portion of our planet's water, filling our oceans. So, the next time you take a sip of water, you might just be tasting the ancient remnants of a long disintegrated asteroid shower. A rather humbling and slightly gritty thought. Even more excitingly, these samples are rich in organic molecules. Not life itself, mind you, but the building blocks of life. Amino acids, the components of proteins, nucleobases, the components of DNA and RNA, and other complex carbon compounds. And critically, the types and varieties of these molecules found in the asteroid samples closely match those found in certain types of meteorites that have fallen to Earth, and they show telltale isotopic signatures that confirm their extraterrestrial origin. They weren't just contaminated after landing. This is powerful evidence that the raw ingredients for life weren't unique to Earth. They were widespread in the early solar system, cooked up by natural chemical processes in the protoplanetary disk and on the surfaces of these small bodies, then delivered to young planets like ours. It's like the universe was running a cosmic mail-order service for prebiotic chemistry. Special delivery, 1 planet's worth of amino acids. Assembly required. Studying comets, those icy wanderers from the further reaches of the solar system, complements this picture. Missions like ESA's Rosetta, which orbited and landed on Comet 67P/Churyumov-Gerasimenko, have given us incredible insights into their composition. Comets are also rich in water ice, though often with a different isotopic fingerprint than Earth's water, suggesting they might not have been the primary source of our oceans, but certainly contributors, and a plethora of organic molecules, some surprisingly complex. They are like dirty snowballs, yes, but exquisitely preserved, fluffy snowballs containing clues to the chemistry of the cold, outer regions where they formed. These missions also help us understand the evolution of these small bodies. We see evidence of space weathering, how their surfaces are altered by eons of exposure to solar wind and micrometeorite impacts. We learn about their internal structure. Many asteroids appear to be rubble piles, loosely bound collections of smaller rocks and dust, rather than solid monoliths. This is crucial information for understanding their history, and also for planning any future efforts to, say, deflect an asteroid that might be on a collision course with Earth. Knowing whether you're trying to nudge a solid boulder or a cosmic beanbag makes a rather significant difference to your deflection strategy. Nobody wants to be the cosmic equivalent of trying to herd cats with a cannon. So, as you settle into the stillness of the night, imagine these small ancient wanderers. They are not just hazards, they are historians. They carry the chemical memory of our solar system's birth. Each grain of dust returned by Hayabusa 2 or OSIRIS-RX is a tiny, precious whisper from the past, telling us about the water we drink, the organic molecules that form the basis of life, and the very stuff our world is made of. They are the unsung and often unglamorous heroes of planetary formation, the cosmic messengers who delivered the goods. And sometimes, yes, they are also a stark reminder that the universe occasionally throws rocks at us. But tonight, let's focus on their more constructive, life-giving contributions. Sweet, dusty, and slightly organic dreams. From the ancient dust of asteroids and comets, let's now turn our sleepy gaze a little closer to home, to our constant celestial companion, the moon. It hangs there in our night sky, a seemingly serene and unchanging presence. But its pale, cratered face hides a fiery, violent youth. And recent studies, particularly those analyzing lunar samples brought back by the Apollo missions decades ago, combined with new remote sensing data from lunar orbiters, continue to strengthen a dramatic hypothesis about its earliest days. The moon, shortly after its formation, was likely covered by a global ocean of molten rock, a lunar magma ocean. Forget gentle seas of water. Imagine a roiling, incandescent sea of lava hundreds of kilometers deep. Our calm, silvery moon was once a hellish, glowing ember. The leading theory for the moon's formation is the giant impact hypothesis. A Mars-sized protoplanet, often dubbed Theia, collided with the early Earth in a cataclysmic, planet-reshaping event. The debris from this colossal smash-up was flung into orbit around Earth and eventually coalesced to form the moon. The sheer energy involved in such an impact would have been immense, easily enough to melt a significant portion of the newly formed moon, creating this global magma ocean. It's a rather dramatic birth story, isn't it? Our moon isn't just a sibling. It's more like a child born from a planetary fender bender of epic proportions. Sorry about that, Earth, just rearranging the cosmic furniture a bit. Here, have a moon. Evidence for this magma ocean comes from the composition of lunar rocks, especially the anorthosites that make up the bright lunar highlands. These rocks are relatively light, rich in a mineral called plagioclase feldspar. The idea is that as the vast magma ocean slowly began to cool and solidify, plagioclase crystals, being less dense than the surrounding melt, would have floated to the surface, like cream rising to the top of milk, or perhaps more accurately, like rocky slag floating on a molten metal bath. Over millions of years, this process would have formed a thick, anorthositic crust. The very highlands we see today as the brighter, more ancient parts of the moon's surface. It's like the moon formed its own little igneous iceberg crust from a sea of fire. The darker regions of the moon, the Maria, Latin for seas, so named by early astronomers who mistook them for actual bodies of water, a rather optimistic if inaccurate assessment, are younger basaltic plains. These were formed by later volcanic eruptions, where magma from deeper within the still partially molten mantle breached the surface and flooded large impact basins. But the underlying story of the initial global melt remains a cornerstone of lunar science. Analyzing the trace elements and isotopes within the Apollo samples provides further clues. The specific patterns observed are consistent with the kind of chemical differentiation that would occur as a massive body of magma slowly crystallizes. Scientists can even estimate the depth of this magma ocean, with current models suggesting it could have been hundreds, perhaps even over 1,000 kilometers deep. Imagine standing on the early Earth, if you could somehow survive the equally hellish conditions there, looking up at a moon that wasn't a gentle silver disk, but a glowing orange-red orb radiating intense heat, its surface a churning, convective inferno. It would have been a truly awe-inspiring and terrifying sight. Our tides would have been significant, and probably molten. This concept of a magma ocean isn't unique to the moon. It's likely that Earth too went through a similar phase in its early history, due to the energy of its formation and frequent large impacts. In fact, magma oceans might be a common stage in the formation of rocky planets throughout the universe, a sort of fiery baptism that sets the stage for later geological evolution. It's a reminder that planetary birth is not a gentle process. It's often violent, messy, and involves a lot of melting. So, next time you look up at the moon, serene and silent, remember its tumultuous past. That calm, pockmarked face belies an infancy spent as a seething ball of molten rock. The craters are just the scars of later bombardments, superimposed on a surface that was once entirely fluid, entirely incandescent. It adds a certain dramatic flair to our celestial neighbor, doesn't it? It's not just a dead rock, it's a retired volcano of planetary proportions, now enjoying a very, very long cool down. Let this image of a fiery young moon gently rock you towards sleep. The contrast between its violent, molten past and its current, cool tranquility is a testament to the vast timescales of cosmic evolution. What was once a raging inferno is now a quiet, reflective companion. It's a reminder that even the most extreme conditions can, over eons, give way to a kind of peace. The universe has a way of eventually turning down the heat, of letting things settle. And in that slow cosmic cooling, there's a profound sense of stability, a promise of eventual calm, even after the most spectacular of fiery beginnings. The moon, our glowing ember turned to silver, is a beautiful, silent witness to that truth. Having basked in the ancient, fiery glow of the nascent moon, let's now stretch our minds to the very edges of the observable universe and grapple with a cosmic conundrum that has astronomers scratching their heads, muttering into their coffee, and occasionally checking their calculations with a distinct air of bewilderment. We're talking about the Hubble Tension. It sounds like a particularly stressful yoga pose, or perhaps the feeling you get when your in-laws are staying for an extended visit, but it's actually a significant discrepancy in measurements of the Hubble constant, the rate at which the universe is expanding. And the fact that different, well-established methods are giving consistently different answers is hinting that there might be something fundamentally new to learn about the cosmos, or, more unnervingly, that we've missed something rather important in our understanding of how it all works. So what's the issue? Edwin Hubble, back in the 1920s, discovered that the universe isn't static. Galaxies are, on average, moving away from us, and the further away they are, the faster they recede. The Hubble constant h0 quantifies this expansion rate. Knowing its precise value is crucial for determining the age, size, and ultimate fate of the universe. It's a cornerstone of modern cosmology. You'd think after nearly a century we'd have it nailed down. Apparently, the universe enjoys a good cosmic practical joke. There are two main ways we try to measure age. One method looks at the early universe, specifically the cosmic microwave background, CMB, that faint afterglow of the Big Bang. Satellites like Planck have mapped the CMB in exquisite detail. By analyzing the tiny temperature fluctuations in this ancient light, and plugging that data into our standard cosmological model, known as lambda CDM, which includes dark energy and cold dark matter, scientists can predict what the expansion rate should be today. This method consistently gives a value around 67 or 68 kilometers per second per megaparsec, a megaparsec being about 3.26 million light years. So, for every megaparsec further away a galaxy is, it recedes about 67 kilometers per second faster. Seems straightforward enough if you ignore the mind-bending units. The other method looks at the late universe, or the universe as it is more locally and recently. This typically involves creating a cosmic distance ladder. Astronomers measure the distances to nearby galaxies using well-understood standard candles, objects of known intrinsic brightness, like Cepheid variable stars, which pulsate at a rate related to their luminosity, or Type Ia supernovae, exploding white dwarf stars that all reach roughly the same peak brightness. By comparing their apparent brightness to their known intrinsic brightness, we can calculate their distance. Once we have distances and measure their recession velocities, via redshift, we can calculate h. This late universe method, using instruments like the Hubble Space Telescope and others, consistently yields a higher value for h, typically around 73 or 74 kilometers per second per MPC. And there's the rub. 67 versus 73. It might not sound like a huge difference to us mere mortals who struggle with tipping percentages, but in cosmological terms, it's a 5 sigma discrepancy. That's a level of statistical significance that makes scientists sit up and say, this is probably not just a fluke or a measurement error. Something weird is going on. The error bars on these measurements have shrunk over the years, but the gap remains. The universe seems to be expanding faster in our local neighborhood than our best model of the early universe predicts it should be. It's like your GPS telling you you'll arrive in an hour based on the early part of your journey, but your speedometer shows you're consistently going faster than expected. Either the GPS is using a faulty map, or your car has developed a secret turbocharger. What could be causing this Hubble tension? The uncomfortable possibility is that there's some new physics we haven't accounted for. Perhaps our lambda CDM model, while incredibly successful in many ways, is incomplete. Maybe dark energy isn't a simple cosmological constant, but something that changes over time in a way we don't understand. A phantom dark energy, or an early dark energy that behaved differently in the young universe. Or perhaps there are new, undiscovered fundamental particles that affected the expansion history, some exotic form of dark radiation. Maybe gravity itself behaves differently on cosmic scales than Einstein predicted, requiring modifications to general relativity. The list of theoretical possibilities is long, creative, and frankly, a bit headache-inducing. Each solution seems to open up a new can of cosmic worms. Of course, there's always the chance that there are still some subtle, unaccounted for systematic errors in one or both types of measurements. Astronomers are an incredibly meticulous bunch, constantly rechecking their calibrations, their assumptions, their data analysis pipelines. But so far, no obvious culprit has emerged to explain away the entire discrepancy. The tension stubbornly persists. So, as you drift in the quiet of your room, let this cosmic speed wobble gently perplex you. It's a beautiful example of science in action. Not a neat, tidy story of answered questions, but a live, ongoing mystery playing out on the grandest possible stage. It's a reminder that the universe is not obliged to conform to our neatest theories. It has its own agenda, its own expansion rate, and it's not afraid to keep us guessing. There's a strange kind of comfort in this uncertainty. It means there are still profound discoveries to be made, still fundamental aspects of reality that elude us. The universe hasn't given up all its secrets yet. It's still got a few curveballs to throw, a few tensions to create. And in that ongoing cosmic conversation, that gentle but persistent disagreement between our measurements and our models, lies the thrill of future understanding. For now, let the mystery be a soft, perplexing hum, a cosmic lullaby of the slightly too fast, or perhaps slightly too slow, depending on your preferred measurement universe. Sleep well in this expanding and ever so slightly puzzling cosmos. Having wrestled with the universe's perplexing expansion rate, let's now delve deeper into the very fabric of that expansion, into the dominant, yet most enigmatic components of the cosmos, dark matter and dark energy. These aren't just minor footnotes in the cosmic inventory. Together, they make up about 95% of the total mass energy content of the universe. Ordinary matter, the stuff that makes up stars, planets, galaxies, and us, the stuff we can see and interact with directly, accounts for a measly 5%. We are, it seems, living in a universe where the vast majority of what exists is invisible, intangible, and profoundly mysterious. It's like discovering that the magnificent iceberg you're admiring is 95%. Well, something else entirely hidden beneath the waves, and you have absolutely no idea what that something else is. Reassuring, isn't it? Let's start with dark matter. We can't see it, it doesn't emit, absorb, or reflect light, hence dark. But we know it's there because of its gravitational effects. Vera Rubin and Kent Ford, back in the 1970s, observed that stars in the outer regions of spiral galaxies were orbiting far too quickly. According to the visible matter alone, these stars should have been flung off into intergalactic space. The only way they could be held in their orbits was if there was a lot more mass present than we could see. A vast halo of invisible dark matter surrounding the galaxy, providing the extra gravitational glue. Similar evidence comes from the way galaxy clusters bend light from more distant objects, gravitational lensing, the motions of galaxies within clusters, and the large-scale structure of the universe itself, like that cosmic web we discussed. The gravitational fingerprints of dark matter are everywhere. But what is it? That's the billion-dollar question, or perhaps, given the scale of the universe, the multi-trillion-dollar question. It's not made of ordinary atoms, protons and neutrons, which astronomers call baryons. If it were, it would interact with light in predictable ways that we don't observe. So, it must be something exotic, something outside the standard model of particle physics, our current best theory of fundamental particles and forces. Leading candidates include WIMPs, weakly interacting massive particles, which are hypothetical particles that, as their name suggests, interact very weakly with ordinary matter, making them incredibly hard to detect, but have significant mass. Axions are another possibility, extremely light, hypothetical particles. Or perhaps dark matter isn't a particle at all, but a modification to gravity on large scales, though most evidence currently favors the particle hypothesis. Scientists are running incredibly sensitive experiments deep underground to shield them from cosmic rays, trying to catch the fleeting whisper of a dark matter particle interacting with a detector. So far, silence. Or at least nothing definitive. The universe is guarding this secret very closely. It's like the cosmos built this enormous, invisible scaffolding and then conveniently lost the blueprints and the list of building materials. Trust us, it seems to say, it's there. Don't worry your pretty little 5% heads about what it's made of. Then there's dark energy. If dark matter is the universe's mysterious gravitational glue, dark energy is its equally mysterious accelerator pedal. In the late 1990s, two independent teams of astronomers studying distant Type Ia supernovae discovered, to everyone's surprise, that the expansion of the universe isn't slowing down, as you might expect due to gravity's pull. It's accelerating. Something is actively pushing space-time apart, working against gravity on cosmic scales. This something was dubbed dark energy. And it's even more enigmatic than dark matter. It seems to be a property of space itself, a kind of intrinsic energy density of the vacuum. As space expands, you get more space and thus more dark energy, which causes space to expand even faster. It's a runaway effect. The most common explanation is the cosmological constant, a term Einstein originally introduced into his equations and later called his biggest blunder, though it seems he might have been right for the wrong reasons. But the theoretical value of this vacuum energy predicted by particle physics is wildly, absurdly, catastrophically larger than what we observe, by about 120 orders of magnitude. This is often called the worst theoretical prediction in the history of physics. So, while the cosmological constant fits the observational data reasonably well, its theoretical underpinning is shaky, to put it mildly, or perhaps apocalyptically wrong. Alternative ideas for dark energy include quintessence, a dynamic, evolving energy field, or again modifications to our understanding of gravity. But like dark matter, its true nature remains one of the most profound puzzles in modern science. It makes up roughly 68% of the universe's total mass energy content. It's driving the ultimate fate of the cosmos, potentially towards a big rip or an eternal, cold, big freeze. And we have almost no concrete idea what it is. It's like being on a ship that's speeding up for unknown reasons, powered by an invisible engine running on mystery fuel, operated by a phantom crew. Sweet dreams. So, as you lie there, embraced by the familiar gravity of Earth, remember that you are swimming in an ocean of unknowns. The universe around you, the very space between stars and galaxies, is dominated by these two dark entities. They shape its structure, drive its expansion, and dictate its destiny. And they remain almost entirely beyond our comprehension. There's a profound humility in this knowledge. We, with all our science and technology, have only managed to glimpse the tip of the cosmic iceberg. The vast, dark bulk of reality remains hidden from us. But this isn't a cause for despair. It's an invitation to wonder. It's a testament to the sheer, mind-boggling richness and strangeness of the universe. It doesn't just exceed our imagination. It often seems to operate on principles that mock our attempts to categorize it neatly. Let the mystery of dark matter and dark energy be a soft, deep, velvety darkness that envelopes you. It's okay not to have all the answers. The universe is vast and full of secrets. And in acknowledging that vast ignorance, in embracing that profound mystery, there is a strange and wonderful kind of peace. We are but a tiny flicker of understanding in a vast, dark, and utterly fascinating cosmos. And for tonight, that's more than enough to lull you into the deepest, most stardusted sleep. And so, as our journey through the latest cosmic revelations nears its gentle end for tonight, let's tune our sleepy senses to one final, subtle, yet universe-spanning phenomenon, the first hints of the cosmic gravitational wave background. We've already touched upon the chirps from individual black hole mergers detected by LIGO and Virgo, relatively high-frequency, short-lived events. But imagine now a much deeper, more persistent hum, a ceaseless chorus of gravitational waves generated by countless supermassive black hole mergers across cosmic history, all overlapping to create a very low-frequency rumble in the fabric of spacetime. This is the Cosmic Gravitational Wave Background, or GWB, and recent findings from pulsar timing arrays are suggesting we're finally starting to hear its faint, primordial song. What are pulsar timing arrays? They are a wonderfully ingenious, galaxy-sized gravitational wave detector. Astronomers use radio telescopes to monitor a network of pulsars, those rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. These pulsars are incredibly stable clocks, their pulses arriving with remarkable regularity. The idea is that if a very long wavelength gravitational wave, the kind expected from the slow dance and eventual merger of supermassive black holes, a process that can take millions of years, ripples through our galaxy, it will subtly stretch and squeeze the spacetime between Earth and these distant pulsars. This will cause a tiny, almost imperceptible, but correlated change in the arrival times of their pulses. Some pulses will arrive a few nanoseconds early, others a few nanoseconds late, in a specific pattern across the sky that is characteristic of a gravitational wave. For decades, projects like NNOGrav, North American Nanohertz Observatory for Gravitational Waves, PPTA, Parkes Pulsar Timing Array, and EPTA European Pulsar Timing Array, have been painstakingly monitoring dozens of these millisecond pulsars, accumulating years, even decades, of timing data. It's a monumental effort, requiring incredible precision and an almost saintly level of patience. And in the last couple of years, these collaborations have announced that they are seeing a common low-frequency signal in their data that is consistent with the expected signature of the GWB. The evidence is still building, the signal is right at the edge of detectability, but it's incredibly exciting. It's like finally hearing the faintest, deepest bass notes of the universe's orchestra, a sound that has been playing since the cosmos was young. What could be producing this background hum? The leading candidate is the inspiral and merger of supermassive black hole binaries. When galaxies merge, a common process throughout cosmic history, their central supermassive black holes are expected to eventually sink towards the center of the newly formed galaxy, form a binary pair, and then, over millions or billions of years, slowly radiate away energy as gravitational waves, spiraling closer and closer until they finally coalesce. Given the sheer number of galaxies and galaxy mergers over cosmic time, the overlapping signals from all these ancient, ponderous dances should create a stochastic or random background of gravitational waves. This is the universe's background hum, a subtle tremor from a billion ancient smash-ups, mostly involving the biggest monsters in the cosmos. Detecting this GWB opens up a whole new window onto the universe. It allows us to study a population of supermassive black hole binaries that are too far away or too early in their merger process to be seen as individual sources. It can tell us about the demographics of these giant black holes, how often they merge, and how that process influences galaxy evolution. It's a new way to probe the dark ages of the universe before the first stars fully illuminated the cosmos, and to understand the assembly of the large-scale structures we see today. And there are other, even more exotic, potential sources for a gravitational wave background. It could contain imprints from cosmic strings, hypothetical defects in space-time formed during phase transitions in the very early universe. Or it could even carry signals from inflation, that proposed period of super-rapid expansion moments after the Big Bang. Teasing out these different potential contributions from the overall hum will be a challenge for the future, but the initial detection of the background itself is a landmark achievement. So, as you lie on the cusp of sleep, imagine this gentle, pervasive tremor in space-time. It's not violent like an individual merger chirp. It's more like the distant, almost imperceptible rumble of cosmic machinery, the collective whisper of countless ancient, massive events. It's the universe breathing on the grandest possible scale. It's a sound that has been traveling for billions of years, a sound that permeates all of space, a sound that we are only now, with our galaxy-sized detectors and our incredible patience, beginning to discern. This cosmic gravitational wave background is a reminder that the universe is never truly silent, never truly still. Even in its deepest voids, space-time itself is subtly, constantly vibrating with the echoes of its own tumultuous history. It's a lullaby of cosmic violence, yes, but also a lullaby of cosmic evolution, of galaxies merging, of black holes dancing their slow gravitational waltz. It's a sound that connects us to the deepest, most fundamental workings of the cosmos. Let this faint, universe-spanning hum be the final sound that carries you into your dreams. It's a sound of immense power, yet incredible subtlety. A sound of ancient events, yet ever-present. A sound that speaks of the universe's ongoing, dynamic story, a story written not just in light, but in the very ripples of reality. And so, our journey through the universe's latest whispers, its newest, most astonishing and sometimes starkly realistic revelations, comes to a gentle close for tonight. We've waded through hypothetical oceans on distant water worlds, perhaps imagining the strange, cold life that might shiver in their depths, or simply acknowledging their vast, beautiful sterility. We've sniffed the alien atmospheres, pondering the chemical clues to life, or just to very exotic, very unbreathable weather systems. We've drifted with the lonely rogue planets, those orphans of the void, finding a strange solace in their sunless, silent passage. We gazed into the fiery abyss of supermassive black holes, photographed in their terrible glory, and tiptoed around their sleeping, potentially awakenable brethren, appreciating the universe's capacity for both patient slumber and cataclysmic alarm clocks. We listened to the gravitational echoes of cosmic smash-ups, the universe ringing like a bell from the collision of intermediate-mass black holes, a reminder of its percussive creativity. We peered back at the universe's baby photos, finding surprisingly mature galaxies in the cosmic dawn, and pondered the fierce, short lives of its very first giant stars, the supernovae that seeded us all. We traced the ghostly filaments of the cosmic web, that invisible scaffolding of dark matter upon which everything is built, a grand, unsettling, and beautiful architecture. We skated over icy moons erupting with hidden warmth, and held ancient asteroid dust in our hands, finding the building blocks of water and life delivered from the heavens, sometimes gently, sometimes not so gently. We revisited our moon's fiery, molten past, a stark contrast to its serene present. We wrestled with the universe's perplexing expansion, The Hubble Tension, a cosmic riddle whispering of new physics or our own profound misunderstanding. We embraced the vast, dominant unknowns of dark matter and dark energy, the 95% of reality that remains stubbornly, perhaps hilariously, beyond our ken. And finally, we tuned into the universe's background hum, the subtle, ceaseless tremor of the cosmic gravitational wave background, a lullaby of ancient, massive collisions. The universe, as we've seen, is not just a place of serene beauty and gentle starlight. It is also a place of bewildering complexity, stark indifference, and events of unimaginable power and violence. It is a place where our most cherished theories are constantly being tested, prodded, and sometimes gleefully overturned. It hands us water in abundance, but also vacuums of absolute zero and radiation that would fry us in an instant. It builds elegant structures out of stuff we can't see, and it expands at a rate that keeps us arguing. It's a cosmic comedian with a very dark, very dry sense of humor. But in acknowledging all of this, the beauty and the brutality, the wonder and the weirdness, the known and the profoundly, deeply unknown, there is a strange and profound peace to be found. Our anxieties, our small human concerns, they shrink in the face of such cosmic grandeur and absurdity. We are tiny, fleeting sparks of awareness in an incomprehensibly vast and ancient cosmos. And that, paradoxically, can be deeply relaxing. There's a freedom in insignificance, a comfort in the universe's utter lack of specific concern for us. It's busy. It has black holes to feed and galaxies to collide. So, as you drift now into the deepest, most peaceful sleep, let these cosmic truths settle around you like soft stardust. Let the wonders inspire you, and let the stark realities, framed by a wry smile, remind you that it's all beautifully, terribly, wonderfully out of your hands. The universe will continue its grand, indifferent, and astonishing dance, whether we understand it or not. And tonight, in the safe haven of your mind, you are simply an observer, a dreamer, drifting on the gentle tides of cosmic revelation. Sweet dreams, cosmic voyager. The universe will still be here, full of absurd and beautiful surprises when you wake.